Fine. So yeah. So as I was mentioning, so I hope you, what is this? I hope you appreciate the analogy between the current flow and the water flow, and the way we started this building this started introducing this device. Okay. So yes, yes.
For you drew that graph of ISD versus PSD, that was the straight line passing through VDSD.
Yeah.
So now when we have subtracted the minus half PSD square part, so then the x-intercept will shift.
Okay, right. So let's, I'll draw the graph again, then you can make the point, right? So his point was about, initially we started off with this equation, and then we added an extra term. How will the curves change because of the addition of that extra term, right? So let me sketch those curves again, then hopefully it will answer the question. So since Ig is equal to 0, right? So the input part of the amplifier, we don't have to bother. So Y11, or input part, the input characteristics of the device, we don't have to bother, because Y11 and Y12 actually go to 0. But we'll have to see how the output characteristics play out. That is, we have to plot ISD with respect to VSG and VSD, so that we can take the appropriate differentials, right? So if we take the differentials now, or if we plot the ISD versus VSD, so what did we see? We did this in the last class, so I'll go slightly quicker. So if I plot this, so for, let's say, VSG as a parameter, so VSG equal to VSG1, I am essentially starting from VSD equal to 0 and going to higher values of VSD. So essentially, I am starting off with plotting this equation and then migrating to this equation as and when I breach that limit. Okay, so if I start off with that equation on the top, for very small values of VSD, what would I see? I would see only the linear part being the dominant term. So we will see a linear increment, right? And hence it's also called a linear region of operation. And then if we keep on increasing VSD, you will see a parabolic nature kick in, right? Or rather becoming prominent. And then at some threshold voltage or some critical voltage, which is equal to VSG1 minus VTHP, it will hit saturation and the current will no longer increase, right? So this is for one value of VSG. If I increase the value of VSG, or let's say I decrease the value of VSG, so let's say I decrease the value of VSG to VSG2, then again a similar curve will come into picture, but everything will change slightly, right? Because now we are lowering the value of VSG. So if I lower the value of VSG, then you see both the current equations in both these regimes are going to change, right? It's easier to see how it is going to change in the saturation region, because we don't have any dependence on VSD. And as you clearly see that the value of the current will in fact reduce. So let's start off and say that it has reduced. And if I now switch our focus to the top equation, that is in the linear region, there also you kind of see that at very small values of VSD, that is when the first term is a dominant one, you still see that the current has reduced with respect to the previous one. So essentially, this should start off with a shallower slope, and these two curves will meet somewhere. And that meeting point is the new VSG minus threshold voltage. The meeting point is not the same, right? So essentially, the edge of saturation region changes based on VSG. Okay, so in this case, the edge of saturation region will probably be somewhere here. This will be VSG2 minus threshold voltage. Okay, so now when you are designing an amplifier, so the whole purpose of going through all these things is to find an operating region where I can get an amplifier, good amplifier. So clearly you see that the good region of operation, or rather the region of operation that will give us amplification, is that flat portion, right? In that flat portion, we get y22 will be equal to 0, right? So this is where we should be able to, we should be operating in. Now, the issue becomes, that, let's say I bias my transistor somewhere over here. The operating point is in my control. I choose the operating point somewhere over here. Okay, for this value of VSD, then I can decide, depending upon the value of VSG, that the source to gate voltage, right, which curve should I select, right? Or rather, at what current should I bias my transistor? So naturally, you see there is an issue. The issue is if I choose to bias the transistor at a higher current, right, which means I'm choosing the black curve, you will run into the problem of a smaller range of operating condition for which the transistor is going to operate in a saturation region. Because ultimately, so let's say I haven't shown the maximum limit of VSD, but typically the maximum limit of VSD is limited by the battery that you have used. So let's say the battery voltage somewhere here. You cannot go this side. This is forbidden because the battery will not allow you to. So which essentially means that in order to get a good amplifier, you have to be within, this is the upper limit. And if you choose to operate on the black current curve, so this is the lower limit, right? And if you choose to operate on the purple curve, then this is the lower limit, right? So you see that there is when you decide to choose an operating point, you are also inherently making the decision of what is the range of what is the range of VSD for which your amplifier is going to work. Okay, and ultimately, what is the aim? The aim is to maximize the range also. It's not as if you would like to have an amplifier which operates only at one very sweet biasing point, and you change the operating point slightly and everything goes for a toss. That's not a good design is, right? So ultimately, the good design should have you should have a range of, you should allow for a range of variations, right? So in certain ways, the choice of your operating point is also kind of deciding how much variation you can tolerate. Okay. Okay. So now the question might be, it seems like the purple curve gives me the higher range. Why not choose the purple curve? Right? Why not choose the VSG equal to VSG2? Why bother with the higher value of VSG? Right? So that's the natural question. The answer to that will lie in the other curve. That is, if I plot ISD versus VSG. When I plot this, I'll have to assume that VSD is constant, the source to drain voltage is a parameter. So let's assume VSD is equal to some VSD1. So till I reach a threshold voltage for the source to get, no issues, the current is 0. Now, if I increase the source to gate voltage beyond the threshold voltage, let's say this is VTHP. Okay. So can you comment on which region of operation I will end up being? Will I be in the saturation region of operation, or will I be in the linear region of operation? Or rather, what I'm asking is, will I be looking at this equation, or will I be looking at this equation? Just around VSG, slightly higher than threshold voltage. So let me take some values, probably that will help. So let's say threshold voltage is 0.5 volt, right? I choose VSD1 equal to 1 volt. Okay, so now I am just around, let's say 0.51 volt or 0.52 volt. So do you think it's in saturation region or in linear region? It's in saturation region of operation, right? Good. So essentially we start off from the bottom equation. right? So we start off from the bottom equation. So this becomes a parabola. And how long, till what value of VSG can I keep on increasing VSG before it runs out of saturation region? So which condition am I looking at now? So there is only one condition, right? This guy. Depending on greater than or less than, depending upon which region you are looking at. Yeah, right. So VSG should be less than equal to 1.5, right? So essentially, I am varying this one. I am varying the VSG and I'm trying to figure out what is the limit of VSG. If I keep on increasing VSG, I'm violating that limit. So that borderline condition is VSG equal to 1.5. So till 1.5, this will be kind of a parabola. But after that, I am hitting the other equation, right? I'm hitting this equation. Okay. So, I mean, that is also kind of I mean, now if I hit that equation, then you see that with respect to VSG, that's a linear curve, right? So I will be doing this. Okay. So now if I change VSD, let's say I change VSD to VSD2, which is equal to, let's say, let me increase it, right? So let's say 1.5 volt. Can you comment what the new curve will look like? Let's start off again from somewhere over here. What will it look like? Yeah, it will, but it will, it will follow the initial parabola, right? So it will follow the initial parabola because, I mean, when in saturation, the current is not dependent upon VSD, right? It's independent of VSD. That's what gives the Y22 equal to 0, right? So it's independent of VSD. So this guy will keep going. And then at probably 2 volt, wherever the 2 volt might arise. So let's say this is definitely not up to scale, but you get the idea. So this will go like this. Okay. So now, does this answer your question? So now, now if I take a step back and ask you, if I switch our attention to this curve now and ask you, what happens if I go from the purple to the black curve? Y22 doesn't change. Y22 is still 0 in saturation region. But can you comment on Y21? So what is Y21? What is the expression of Y21 in saturation? Which equation am I looking at? I'm looking at this equation. Right? And I differentiate that. So what should I get? I get mu P Cox W by L VSG minus threshold voltage. So how is Y21 dependent on VSG? It's increasing, right? If I have to increase the Y21, I have to increase VSG. And if we recall the 2-port parameter for our amplifier, we wanted Y21 to be as high as possible, right? So there is an incentive to increase VSG because increasing VSG will give us more Y21, right? So now you see the designer's dilemma. If I want to go this direction and to go that direction because that is giving me more Y21, but going to higher Y21 also means that the range of operation, right, for which I can bias the amplifier is also reducing. Okay, so So essentially, depending upon the application that you are after, you will have to make a choice. Okay, you have to make a choice whether the limits, or these are called swing limits, right? How till what range your signal can swing, the swing limits, what swing limits are tolerable to you and what is not. Okay, so we'll get to the details of swing limits later on in the course, but this is something to be mindful of. Okay, so now enough of graphs. Let's get into some design. So to summarize, the incremental model of a P-MOSFET look like this. So this was the gate, this was the drain, this was the source. In this case, if I, so let's see. Let's not put the drain that side. Let's put the drain this side because that's how we have been doing. So this becomes, the good thing about our case is, let me draw the gate here. The good thing about our case is Y11 and Y12 is 0. So you don't have to bother about anything to be connected at the input side. But on the output side, we have Y21 that is necessary. So it becomes Y21 times VSG. And again, what is the direction of the current? Upward, downward, downward. Easy way to remember, if I increase the source voltage, the source to drain current increases, right? If I increase VSG, the source to drain current increases. Do I have to bother about Y22? No, Y22 goes to 0. So this becomes a very simplified version of our incremental model of the transistor. So this essentially is the two-port equivalent of the transistor. Okay, two-port incremental equivalent of the transistor. So wherever you see a transistor which is biased in saturation region, that is a critical distinction to make. If the transistor goes from saturation to linear region, this will not be the two-port equivalent because you cannot neglect Y22 then, right? Because the curve is no longer flat. So then the Y22 will appear. A non-zero value of Y22 will appear. Then you have to modify the incremental network. So as long as the transistor is in saturation, this is the model that we can use. Okay, fine. So if this is an incremental model, and let's assume we concentrate on the incremental model only, right? So we want to make an amplifier out of it. So when we have an amplifier, we have a source and we have a load, right? So where do you think should I connect the source first? So again, I would request you to connect it to the initial two-port network that we had. So initial two-port network, the one that we did like 7 classes back probably, was this. The source was connected here and the load was connected here, right? So if I want to do the equivalent of this, so where should I connect the source? Between S and G, right? Because ultimately this is Y21 times this V1, right? This was V1, right? So in our case, VSG is supposed to be V1, right? So between S and G, I should connect the input. So I connect VI here, but in this case, as you see, I have to connect it the other way around because the source is upwards. Okay. But the other important thing that we saw in the incremental model when we were doing our transistor equivalent was okay. So before going there, so now so let's keep it like this. Then I will make the point that I was trying to make. So let's keep it like this for the time being. So what is the load connected between now? Between source and drain. So I can simply connect the RL here. Right. So and this becomes the ESG. This becomes the incremental equivalent of an amplifier using MOSFETs, right? But we all know that this is an incremental equivalent. This is not an actual circuit, right? So if I have to design the actual circuit, I have to go back to this guy and then see how I can garnish that the symbol of the MOSFET, add stuff so that we realize this incremental equivalent. Now note that when I make that statement, I am essentially saying that I have to not only add these RS, RL, VI, but I have to ensure that when I am adding all these components, all these extra stuff, the bias point of the transistor is still in saturation, right? If we don't respect the bias point, the transistor will not behave like whatever we want it to. So the first thing probably should be then to ensure that the transistor is in saturation, and then go ahead and add the inputs and the outputs the way we want them to. Okay. So let's first address that, right? So we have to ensure that the transistor is in saturation. So let's first address that. So we need some reference as always. And if I again go back to the analogy of this reservoir, right? What is the reservoir equivalent in terms of electronic circuit? It's a battery, right? So the battery, in the reservoir equivalent, the battery, in that pipe equivalent, the reservoir is connected to the source. So in this case also, then it makes sense to connect the battery to the source. So we'll connect a battery to the source. Let's say it is some VDD or VDC, let me say for the time being. VDC. Okay. Let me take some values. So let's assume the threshold voltage is 0.5 volt. This is, let's say, 3 volt. Okay. So can you comment on can you comment on a value of the gate voltage which can lead to the saturation region operation? Any gate voltage, because we don't yet have enough information. Okay, let me ask you this. So this is 3 volt. If I select the gate voltage to be 3 volt, will the transistor work? No. Why will it not work? Because VSG is less than threshold voltage, right? The tap is not on. The tap is fully off, right? So what is the minimum that I require? 2.5, right? But if I go back 2 classes back, you remember I made a point, all these equivalents are valid only when you are like 100 millivolt at least away from being on, right? It's not as if it suddenly goes on and suddenly goes off. So you have to give some margin. So minimum should be then 2.4, right? So let's assume this is 2.4. I mean, let's round it off, make it 2 volt. Okay, so fine. So now with this, we only know that the transistor is on. We don't yet know if the transistor is in saturation, right? So what determines if the transistor will be in saturation or not? Yeah, rather the drain voltage, because the source is constant, right? So we have fixed the source, we have fixed the gate. Basically, the drain voltage will determine. So now, can you tell me what is the minimum or maximum drain voltage? First, you have to understand whether we are looking for a maximum or looking for a minimum for the drain voltage. So let's say drain voltage is 3 volt. So do you think the transistor is in a linear region or it's in linear region, right? Good. Just another question, which is not particularly related to this. What is the current through the transistor? If this is how it is biased? 0, right? So is the transistor on? When I say on, I essentially mean that the channel is formed or not. Channel is formed, which means the transistor is on, but the current is 0, right? Because VSD is 0. Okay, fine. So it's in linear region, no issues. So I don't want it to be linear region. So what should I do? Decrease the drain voltage. How far should I decrease? At least 2. Which is in this case? Right. So essentially 2.5, I should have it at 2.5, right? So if I have it at 2.5 volt, then the transistor is in saturation. Then that other current equation, right? Mu P C ox VSG minus threshold voltage whole square will become valid. All good. So now we are satisfied the transistor is in saturation. We'll have to connect a source, right? So let me make this 2 volt. Instead of making this 2 volt like this, what I'll do, I'll just say that I put a 1 volt battery between VSG, because that's what essentially is giving us the effect of transistor being on, right? The VSG is the important stuff. Okay. Transistor is in saturation. Now we have to add the load and the source. So let's see how can we add the source first. So where can I add the source? Firstly, I have to add the source at the gate, right? Because here in the incremental model, we added it at the gate or between the gate and the source, right? So in this case, how should I go about adding it? Pardon? In series with the 1 volt, 1 volt source. So essentially, we put it in this format. So quick comment, do you have any current through this? No. So essentially, the drop across RS is 0. So having RS or not having RS doesn't really matter. Okay, so the input is set. What about the output? I have RL to be attached. In this case, the RL was attached between the source and the drain. So what should I do now? Come again? Didn't hear you. Okay, you mean between here and? Okay, you mean here? Okay, interesting. But here we assume that these are all grounds, right? This terminal were grounded. Okay, you don't want the ground to be here. You want the ground to be this. Okay. Okay, so let's think about this for time being. Okay. So what effect will this have? So initially we had the current, which was the saturation region current, which was half mu P Cox ESG minus threshold voltage whole square. Let me put some value times W by L, right? Time is W by L there. Okay. So let's put some value. Let's say this is approximately 1 milliamp. Okay. So when we started off, when RL was not there, it was only biasing, it had 1 milliamp. So now let's see what application of this RL will do. So let's say this is 1 milliamp, all good. So this 1 milliamp goes here. So this 1 milliamp is traveling through the load, right? It's closing the loop. So it has to go this way only. So it cannot go into this ground. Correct? So if this is 0 volt, so this voltage will be 1 milliamp times RL, right? So this will be whatever ID sat, that is saturation region current times RL, which means the source voltage will be 3 volt plus. So this voltage will be 3 volt plus VD sat times RL. So as you see, the source voltage now dances, right? So which means that if the source voltage dances and the gate, so that's not necessarily always a good thing, right? So because ultimately you want some stability in the voltage. Essentially, what is this is supposed to be? It is supposed to be a constant voltage supply, right? So even though it might seem sometimes that it's okay to leave, to have your configuration like this, but we would like to ensure that just like we have a reservoir, we would like to ensure that the source voltage is held constant. Okay, so that is why this particular configuration will probably not be a very practical scenario, even though this configuration in principle is still going to work. Right? So if you draw the small signal equivalent of this, you are going to see that this configuration still works. But there is a practical problem with this. The practical problem is that there are multiple practical problems with this. One of the practical problems is you will see soon that even though I have connected the source, the input side like this, the input reference, right? So this voltage source will should always be referred to ground, because you have done your ESC 201 labs where you have connected some supply, some source and some supply. Both the source and the supplies were never connected in series. If you recall, all of them were always connected with an implicit ground. You had a black wire which was connected between the machines and had to be connected to the breadboard. So that reference wire was the ground. So all equipments, all sources should have a common ground. Even though I have connected, even though I have shown this as a floating source, right? On a piece of paper or a PowerPoint presentation, you can draw anything, but in a practical scenario, you cannot have a floating source. Why am I making all these points? Is that if I don't make this a floating source, right? If I, let's say somehow I have to ensure that one terminal is grounded. So then, and this 1 volt will also not be a floating source, right? So the next thing to do is this. Next thing to do is to say that I have a 2 volt battery. If I put a 2 volt battery which is in series with a ground, I'm not changing anything, right? So, and let's say for the time being, I use this floating source also. So this becomes 2 volt, this becomes RS. So in principle, I haven't changed anything, right? But this is a more of a practical way of bias, or I should say less impractical way of connecting up a circuit in reality. But I'm making all these points because now let's come back to this way of connecting RL. So now what you see is this voltage, the source voltage, becomes 3 volt plus VD sat times RL. What is the gate voltage? It remains 2 volt. So what is the source to gate voltage? The source to gate voltage has now changed. Right? Because the source to gate voltage has changed, all the initial bias points that you had calculated is also changed. Right? So after connecting RL, you do not want the bias points to get changed. Because the source to gate voltage will change, then your current will change, your current will change, means your Y21 will change. Your Y22 can also, I mean, the region of operation, the swing limits, right? The range for which your amplifier will be working might also change, in fact, will change. So once you decide a bias point, you don't want that bias point to get affected after you have added extra contractions to get it to work like an amplifier. Okay, so that is why even though in small signal model, this way of connecting RL will actually work, but when you put everything together, you will see that you will run into this problem of you are trying to satisfy the incremental model, but the quiescent point is getting affected, right? So a part of the job of a designer is the interplay between the incremental model and the quiescent point to ensure that the quiescent point doesn't change, right? But this is a very good, I mean, this was a very good digression which was required. Okay, fine. If this is, even though this way of connecting is probably, I mean, has an issue, what is the other way of connecting? Right. So obviously, I mean, the issue, I mean, one way of thinking about this issue is that I don't want the source voltage to move, which essentially means that I want this VDC to be reference to a ground. Correct? But I want RL in the loop anyhow, because ultimately across RL, I want the incremental voltage, right? So if I connect the RL here, you have a problem. If I connect RL here, you have a problem. Maybe the only place to connect is probably somewhere here or maybe somewhere here, right? I wouldn't want to connect it here because again, we have the same problem. We want the 2.5 volt battery reference to ground. All the batteries should be ultimately reference to ground. Then probably the only place looks like where I can add the RL is here. Anywhere in the loop should be fine. Yes.
Inside, when you add the incremental voltage, won't the 2 volt battery become floating?
Yes, it will. So that is a part of the problem I haven't still addressed, right? So we'll get to that hopefully in the next class. So this RL, let's get rid of from this guy, and we can add the RL here. Okay. But now you can turn around and tell me one thing. What about the drain voltage, quiescent drain voltage after I have connected RL? Is it still 2.5 volt? In the absence of RL, the drain voltage was 2.5. But in the presence of RL, is the drain voltage 2.5? No, right? So what will it be? IDSAT times RL plus 2.5. So aren't we facing the same issue all over again? I mean, it looks like the bias point is getting affected. And if I had biased this at 2.5 volt, clearly IDSAT plus 2.5 is higher than 2.5, which means the transistor goes into linear region, right? So what is the solution? Can I do something to get the transistor back into saturation? So let's say IDSAT times RL is equal to 1 volt. So which means that, or let's say 0.5 volt, 1 volt, it will go to 3.5, right? So let's say this is 0.5 volt. So IDSAT times RL plus 2.5 is essentially 3 volt. So it's essentially telling me the transistor will be in linear region, and if the models are valid, it's going to get almost zero current, right? But therein you have to, I mean, obviously you see that this is the transistor is no longer in saturation. This equation will not hold. You have to go back and do the linear region operation. But if I don't even want to get into the linear region operation, all we need to understand is that if the transistor is not in saturation, it's useless for an amplifier. So that's all I need to figure out. So looks like the transistor is not in saturation. If I connect the RL and and the 2.5 volt battery the way I have. Is there anything that I can do to bring the transistor back? Yeah, change the voltage 2.5, right? I can essentially say that I can, if an additional 0.5 volt was getting dropped across, was dropping across RL, I can reduce the 2.5 volt battery and make it 2 volt. Right? So I go back to wherever the quiescent point still remains intact. Right? So in this way, what you see is that starting from very first principles, you can design an amplifier. You can design an amplifier for which you still can have the bias points intact while honoring the incremental equivalent that we are after. Okay. Okay. Thank you.